All right, take a look at this diagram down here. So normally when we talk about a distribution in terms of a bell curve, we use x values, right? So we did this before. We did it with height, for example. We have the mean height here in the middle, and then we'd have the distribution. Some people would be really tall on the high end, some people would be really short on the low end. We did it with IQ, right? The mean IQ, and then geniuses, and then people that have low IQs. And you do it with weight. You can use x units, the corresponding data, to create a normal distribution with mean and then variation around that mean. All we're doing here is looking at not height or weight or intelligence, but instead the distribution of sample means. So it's the same principle. You'd have the mean of the sample means here, and you'd have sample means that are really high and sample means that are really low. But you would be illustrating them in x units, the actual data itself. With all of these data sets, height, weight, intelligence, or sample means, we can standardize the data by converting it into z units. Remember, z units are just the number of standard errors that our data will lie from the mean. For example, let's say we want to create a 95% confidence interval. Well, 95% confidence interval would mean we have an alpha of 5%, which effectively means that 5% of our data will lie in the total of both tails. In each tail, though, you'd have alpha divided by 2, so 2.5% of your data would lie up here, and 2.5% of your data would lie down here, leaving 95% in between. From that, we can create this 95% confidence interval by finding the z value that represents the upper confidence level and the z value that represents the lower confidence level. To do that, we go to our z-table. Before we go to our z-table, though, I want to remind you that when interpreting a z-table, if we're looking for the positive z-score, we start with the lower tail and find the value that would correspond to the area up to that point, which in this example would be the probability of getting a value up to here, which would be 0.975. Okay? Because all you have left is what's in the tail, which would be 0.025. So there is a 0.975 probability of getting a value from this lower tail all the way up to here. Okay? So that's what we're going to look for in our table, 0.975. Let's do that. I'm going to find 0.975, and here we go. So right here. And you'll notice that corresponds to 1.96. So go back, and you'll notice we have z equals 1.96. Now, because this is a symmetrical normal distribution, the negative z value would be the same, negative 1.96. All right, keep that in mind as we go through these examples. Okay, I went ahead and completed these applications so you have all the information to work through them yourself. However, I do want to walk through how I got these details. So the first one says a sample of 120 randomly selected cars showed highway speeds in a certain location that averaged 66.2 miles per hour with a population standard deviation of 13.8 miles per hour. Find a 99% confidence interval for the average highway speed of the cars at this location. Okay. Now refer back to our actual formula. Let's go back to here. And we know it's the sample mean, x bar, plus or minus the z value that corresponds to the proper confidence level times the standard error, which is the population standard deviation divided by the square root of n. Another way of putting it is x bar, sample mean, plus or minus the margin of error, which is just this here. So with that in mind, Let's go back. Well, what does our sample mean? Well, it's 66.2. It says we sampled 120 randomly selected cars, and the average was 66.2. So we've got that. Plus or minus the z-score times the standard error. Well, the standard error is straightforward, right? You take the population standard deviation of 13.8, that's our numerator, divided by the square root of our sample size, which is 120. So we got that. But where did we get this 2.57? You'll notice in our diagram here, if we're looking for a 99% confidence interval, that means we're going to have 1% alpha, right? Because the difference between 100% and our confidence interval is the alpha. And then that means we're going to have 0.5% in each of our tails here, right? 1% divided by 2, 1% divided by 2. So we can see that the z-score positive that's going to correspond to this particular confidence interval is going to be the probability of getting a value up to this point, which is going to be 0.995. Because think about it, the probability of getting a value from this left tail all the way up to here is 1 minus this. 1 minus 0.005 is 0.995. So we're going to go to our z table, and we're going to find that, 0.995. So let's see here, 0.99464849, 0.995. So either one of these would work. Let's go with this one. They're both equidistant. Let's do 0.9949. And the result is 2.57, right? 0.9949, 2.57. And that's the z-score we have. Now it's symmetrical, which means the lower confidence level z-score would be negative 2.57. Okay, so we've got 66.2 plus or minus 2.57 times the standard error. This times this is the margin of error, which is 3.24. Once we have that, we can create our confidence interval. You could leave it like this, that would be fine, but sometimes it's nice to see it in our diagram. Just as we have the upper confidence level for the z-score and the lower confidence level for the z-score, we could have the upper confidence level for our x bar and the lower confidence level for our x bar. 66.2 plus 3.24 would give us an upper confidence level of 69.4. And 66.2 minus 3.24 would give us a lower confidence level of 62.9. So what does all this mean? Well, you went out, you selected a random sample of 120 cars, okay? You got a 66.2 mile per hour. That's your point estimate. But more accurately, we can say that we are 99% confident that the true population mean is between 62.9 and 69.4. Okay? That's how we interpret this data. All right, let's do the next one. So the next one says, a recent study of 38 college students found they spent an average of $275 per semester for books with a population standard deviation of 28, finding 90% confidence interval for the average amount spent per semester by college students. Same process. Okay? What we want to do here is first find our x bar, which is going to be, right, we have a 275. That's our sample mean. So 275 plus or minus our z-score, we'll derive that in a minute from the table, but it says 1.64 times the standard error, which is our population standard deviation of 28 given to us, divided by the square root of our sample, which is 38. Okay? These two combined create our margin of error of 7.45. So we are 90% confident that the true population mean is 275 plus or minus 7.45. That's the way we would interpret it. But let's see how we got this z-score. Well, again, it's a 90% confidence interval. So what we need to do in our diagram is create 90% here in the interval, which leaves 10% in the tails. Our alpha is 10%. Then we divide that 10% by 2 to get 5% in the lower tail and 5% in the upper tail. Then we find the z-score that corresponds to that. Well, the positive z-score is going to be from our z table the probability of getting a value up to this point, which is 0.95, right? 95%, because 5% is in this upper tail. So let's go to our z-table and look for 0.95. So here we have two that are very close to each other. So we could use either one. Let's go ahead and use this one here, 0.9495. And that gives us 1.6, 1.64. Okay. Let's use 1.64. And it's symmetrical, so the negative z-score would be negative 1.64. Then we could convert these z-scores into a range of x values. Take the 275 plus 7.45, our margin of error, you get 282. Take the 275 minus 7.45, you get about 267. So we are 90% confident that the true population mean is between 267 and 282. So what if we don't know the standard deviation of the population, which is going to be more common than not? The only thing that's going to change in our analysis is, instead of using the z-tables to find our margin of error, we're going to use what's known as the t-tables, or t-distribution. This is a distribution that introduces extra uncertainty because we don't know the population standard deviation. In other words, we don't know how the population is distributed. And consequently, we're going to have more uncertainty and a larger margin of error. So the t-distribution is actually a family of distributions that varies with what's known as the degrees of freedom, our sample size minus 1. Okay. And you can see an illustration here. So for example, if you have a t distribution that has 5 degrees of freedom, meaning your sample size is 6, it's going to look like this, the red line. Yeah. On the other hand, if you move your sample size up to 14, you get a degrees of freedom of 13. The distribution becomes a little tighter, the blue. And then if you move your degrees of freedom up to infinity, you would end up with the standard normal distribution, the z distribution. So as we increase our degrees of freedom, which is the same as increasing our sample size, eventually the t will become z, which means that above a certain sample size, you can just use the z distribution. And it's generally thought to be 30, but we'll talk more about that later. Okay, the process moving forward is very similar to what we did with the z value. You're going to have a x bar sample mean plus or minus whatever t value you get based on the degrees of freedom and your alpha divided by 2, that is the tails of your distribution, times the standard error. Now note here that the standard error numerator is the sample standard deviation, not the population. That's the whole idea. We don't know the population standard deviation. We don't know how that population is distributed. So we use the sample as a proxy for the population. But because we're using the sample to estimate the population standard deviation, that's extra uncertainty. And that's going to create the need to use that t distribution. Okay? Denominator of your standard error is the same, square root of n. If you take this times it by the standard error, you get x bar plus or minus the margin of error. And from that, you can create your lower confidence level by taking your sample mean and subtracting, right, the margin of error. Or you can find your upper confidence level by taking the sample mean and adding your margin of error. All right, I'll stop there. In the next video, we will do the applications.